to give you a brief outline of the work I'm going to accomplish. So one thing is basically is introduction and research goal of my work. And then we're going to jump to recycled rubber research from lab and numerical simulation. And then we're going to move to demonstration projects to the field. And then the last one, we're going to really briefly provide a summary. So introduction part really start with U.S. scrap tire disposition. So basically in the past, every year, U.S. generates about 4 million tons of tires, which is equivalent to more than 255 million tires. And of that, there are 43% are used as tire-derived fuel. So basically that means they are going to be burned. And the 25% are used as ground tire rubber. Ground tire rubber has been used in many ways. Maybe they're making new tires, or maybe they're making that new asphalt. But really, for new asphalt, there are really only small percentage. And you can see on this picture here, 16% has been disposed or has been buried underneath the landfills. So that's basically a big portion. There are also some has been sold, exported to overseas, to somewhere. Okay, so basically that's supposedly, those tires, there are a lot of values we can use. I personally think the ground rubber, this area has a lot of things to do. So basically we can take a fully advantage of these materials. So that is basically our goal today. We're trying to find good ways to recycle tires. So here's the tires. So basically we are trying to do is ground tire rubber. Basically we break down tires to small pieces. For example, several pieces like here, you can see basically to small powders. Anywhere from 30 to 50 mesh will be pretty good. So in general, we have 2 processes, one called the dry process, the other called the wet process. So wet process really means you are going to use this powder to make new asphalt in a central asphalt place. Basically, then you basically sell this asphalt product, and the asphalt product can be sent over to asphalt plant to make new asphalt mixtures. The dry process, however, is to directly use dry powders in asphalt plant. That is something we are trying to focus on today. Even though both process, we have been using that one over the years, trying to maximize the application of scrap tires. So then we're trying to do, next is trying to see what the research is about. We are using lab experiments. We also do numerical simulations, which is something I'm going to show here. So here are some kind of typical pavement failures to avoid. When you drive on this type of road, you probably will have some experience. Like this one here is rutting. This rutting, of course, you probably won't really see this type of bad rutting anywhere right now. But of course, this is something happened. It happened in the past. So when you drive on this type of roads, if in the raining day or snowing day, or if you have ice on the roads, it's not really safe at all to drive here. And fatigue cracking, low temperature cracking, this basically add you a lot of experience because you're not uncomfortable when you drive on it, because you can easily feel like you made a lot of bumps and joints, cracks. Those are not really good thing to see. So these are several failures we're trying to avoid. And then, so what are the good ones? The good ones, of course, we need to have some kind of a pavement low temperature cracking resistance. That means if this resistance is available, then we are not going to have low temperature cracking issues. The other is fatigue resistance. We should not have too much of those fatigue cracks. Rutting resistance, of course, this is something we don't want the rutting happening on the roads. It's a structure failure. It's also is a safety hazard. So also we have a moisture damage resistance. So basically for all over the place, no matter how much rain you have, so we all more or less we have experienced some moisture damage issues. For example, on the joke here on the picture on the right hand side, which is a joke, of course, doesn't show you what is the moisture damage eventually is going to do for you. basically you got a lot of potholes, and that's basically very commonly happen everywhere in the world. So that is basically some desired properties we like to see, and that is something we are trying to accomplish in our research. So basically, this is some kind of experimental work we are trying to accomplish here. So basically, we're in this project, we are using rubber asphalt, of course. We're trying to make rubber asphalt mixtures. So basically, we are using the traditional asphalt binder, which is PG 5828 binder, which is commonly used in a lot of places. The second thing I mentioned here is tire rubber. This treated ground tire rubber. This tire rubber is basically using 30 to 50 mesh of rubber particles. We blended it with several fillers and also asphalt binder. So basically this is the new product we are generating. And then basically the finishing up product looks like this. On the left hand side, you can see the particles. It's pretty small particles, but really it's like dry powders. So when we are using these dry powders, basically we are going to inject this one to the asphalt plant. So basically I will have a picture later on to show you. So with that, so basically we use a lot of rubbers, and we use asphalt, and then we use a lot of aggregates. So for example, 95% by weight is basically aggregates, which are stones. And then we make asphalt mixture. You can see on the right hand side, you see this paver. Behind the paver, this is asphalt mixtures. So this mixture right now, you have a lot of rubber, a lot of aggregates, of course. So basically, that is basically the materials we are studying here. So we are testing a few properties. For example, is performance testing for asphalt mixtures. We want to make sure the material we have good rutting resistance. That means under many truck traffic, there should not be much ruts. And moisture sensitivity. That means if we have in the moisture raining time, we don't really have issues. We don't have potential to have potholes at all. The third thing is basically low temperature cracking resistance. So basically, we really want to make sure under low temperature season, you should not have much cracks. So that is basically the several things we are trying to monitor here. And of course, we also have some performance analysis, for example, statistical analysis, numerical simulations, and also we are going to have some field testing work done, because we are moving our design from the lab to the field. So basically, we want to make sure in the field application is good, writability, noise level, everything is super. So that is something we are trying to accomplish. So here is basically something we are talking about some testing. And the testing, these two devices, you see these two devices are basically tested rutting resistance. And either one of these are going to work. So basically this sample here, we call it APA. Of course, this machine called APA, we have samples like 1, 2, 3, you see the same samples. And we have wheels apply on it. Actually, we have a rubber hose on it. So basically you apply load on it, go back and forth. You can see the sample you generated ruts here. And also for this sample, for this machine here, we call hamburger testing device. You can see here the samples placed down here, and you have wheels apply on it back and forth, and then generate the ruts. Take a look at the picture on the right hand side. There are two samples. Both samples, you have some ruts right now after many cycles of load. You can see one with mixture without rubber. So that means this is a conventional asphalt mixture. And the rear corner here is basically the asphalt with rubber. So obviously we can, from our eyes, we can really see with rubber, we have less ruts being generated. That means this material with rubber is better than the conventional asphalt. So of course, during the test, we control a lot of parameters. We control temperatures to make sure the water is also being controlled, or moisture being controlled, loading level being controlled. That is basically, we want to make sure the comparison is fair. Another test we want to really take a look at here is called the split tensile test, or indirect tensile strength test. Basically, during this test, of course, you can see the sample is loaded up like this here, and then the asphalt mixtures being, being tested. After tested, of course, the sample be splitted. They basically we measure the strength, And we also can do a lot of computer simulations, like you see here on this picture here. This is something I did with discrete element models. So that is basically called the split tensile test. We have another type of setup we call the disc-shaped compact tension test, or DCT. So during the DCT test, of course, this is a setup. You can see we load the sample, we load the directions over horizontally, as you can see on the picture, and we can also measure the crack mouth opening distance, which we call CMOD. We measure the load being applied, and also measure the CMOD distance. So basically, that is a picture basically of the on this corner. You can see the sample. This is cylindrical sample. Okay, we cut one edge here, one corner off, and basically have a drill two holes. These two holes eventually are going to be used to apply load. And we also cut a crack. This crack being cut, so pre-cut is crack. And then when we apply load in horizontal direction, so basically the crack is going to be bigger and bigger. So basically we measure the CMOD and we measure the load. That here, the picture here showing you load versus CMOD. So during this test, of course, we can monitor load CMOD curve, and then we can basically calculate this area underneath this curve, and this curve we can call fracture energy. So basically, the fracture energy basically measured how much energy is required to crack the sample. So of course, if for a given sample, if your fracture energy is large, that really means the sample will require a lot of energy to crack it. That means this sample is tough to beat, or this sample has really good fracture resistance. So that is a good thing. That means this sample probably is not going to crack easily for fatigue or maybe for low temperature cracking environment. So basically, this is a DCT test. And we also want to really show you what are some kind of testing results look like. You can see on the right-hand side, on the left-hand side, I basically listed the average fracture energy for a lot of mixtures we designed for this product. You can see we test the materials at minus 24 degrees C, and all the materials are basically on the green are basically all the rubber materials. With the rubber materials, you can see the average fracture energy is roughly more than 1,200 joules per square meter. Actually, quite a few are really, above 1,400. So with these two, for example, 1,400 joules per square meter. But for the conventional mixtures we have here, it's roughly about 400. That means we can easily increase the fracture energy by 3 times or even 4 times. So above 3 times, you can see from several of these things. So basically, that really means the fracture resistance for the rubber asphalt is really good. So that is basically make us really confident we can apply this type of materials on the roads so that we can have really super performance. So now, of course, one question is asking you, why the rubber modified asphalt mixture has high fracture energy? How come? Why that happen? Of course, we did that from a lot of lab work, and also we can verify a lot of things from more experiments and also from a demonstration projects. Of course, here I really want to show you how I really do something to see the insight from numerical simulation standpoint. So with a similar process, basically we can process the aggregates models, make that one even more powerful. So basically, we can see we can generate aggregates like the images you can see on the left-hand side here, and also of course we can improve the accuracy of the models by. So basically during the aggregates project, so after the aggregates model being generated, now we are trying to do is to see how these tests being simulated. So basically here is the DCT samples. You see this before the test. Over here is after the testing. So during the testing, of course, you see the CMOD gauge is going to be continuing increase. Of course, the distance is increasing over the load. And so basically, here's the sample. One of the sample you can see is the top view. So basically, there are red color and the yellow color basically are the aggregates. And so basically the blue color is basically asphalt materials. And of course, we can also say on this picture here, you can see some kind of like some colors here basically showing you what the rubber is. So basically, during the testing, we can really monitor what is a displacement, what is contact force during the process. Well, I will show you for a few things here. So here's the picture basically showing you the fracture path. So basically, during the test, of course, this is a three-dimensional models. During the process, you can see each particle's movement. You can see there how much cracks being generated, and you can see how much force between the particles being generated. And of course, on the over here on the very left-hand side, you can see the aggregates different size, asphalt mastic, and rubber particles. Of course, the rubber particles is not on the left-hand picture. It's only happened on the right-hand side. So basically, on the left-hand side is basically asphalt mixture without rubber, so no rubber. And then basically we are trying to see what does the cracks look like. Take a look at it. You can see the crack is starting to be generated, and basically is you can see the direction is basically from the crack opening starting points and continuously horizontally to the edge, and so basically trying to crack the entire sample. So that is basically what is really the cracks really look like. You can see you have a black color, okay, which is aggregate crack, and you also have red, which is mastic, or we call it asphalt cracks. So basically that is a process. Let's take a look at it with rubber. With rubber, you can see basically the process is a little bit different. You can see the crack is not really just move on to the left hand directly. Instead, it's going to be break down, somewhere in the middle, and then slowly moving toward to the left hand side. So that really means this type of mixture, the fracture resistance is pretty good. So basically, there are a lot of potential to make this type of samples to have a really good fracture resistance. That was the reason this sample has good fracture energy. So, and move on. Next one here basically is a similar picture, but this one I only show you the contact force change. So the left-hand side of this picture here is asphalt mixture without rubber. So without rubber, you can see the contact force is just continuing to move to the left-hand side, and it's basically you got a lot of force concentration. So basically, what we call stress concentration. And with the rubber, you can see the material is basically have some kind of a force, contact force being generated, but really it's being diverted to different locations in the beginning and almost to the ends. So basically that really means this material is much tougher. So basically this is some kind of simulation we have here, and of course we have a lot of simulations work done, and so basically we only show you 2 pictures of this. Our next thing is to move to the field work in the demonstration. So basically, we have research work doing lab work in-house and numerical simulation in-house, and then we are going to move this to the field. So in the field, so basically this project is in Kalamazoo County, Michigan, and so basically the entire road test section was 3 miles, but the 1.5 miles section, basically we are doing the overlay research work. You can see we have conventional asphalt overlay, which is the traditional materials we have. You saw that one is a fracture energy with 400 joules per square meter. And then we are going to use a rubber overlay, which has more than 1,200 joules per square meters of fracture energy. So basically, we are trying to use the rubber asphalt. We are trying to make sure the rubber asphalt's construction is good and the road performance is reliable. So basically, the rubber overlay, you can see we have plenty of rubber inside. So basically, 26% of rubber of the asphalt. That's basically a significant amount, or 2.6% of rubber of the mixtures. So of course, this road originally, was in a really bad situation, a lot of cracks and a lot of ruts. So basically, what we did was trying to mill off the surface, and then basically you can see the close look. Basically, we take get rid of all the top portion, and then basically spray tack coat, and then we'll place overlay on it. So the overlay on it, so basically that's the picture you see earlier on the paver, and the compactor is on this road. And we'll see in the asphalt plant what does the setup look like. So here is basically an overview of a typical asphalt plant. And the major component here is basically dryer and mixer here. So dryer and mixer, which is basically heat up all the aggregates, all the recycled asphalt, and also all the materials meet together, being blended well, and then shipped to the silo here. The silo will basically drop the asphalt mixtures so that the truck can transfer the materials to the job site. Another component in this study is basically the rubber bin. So in the rubber bin, basically what we use the rubber bin and trying to do is the rubber, for example, drop down here, and then we just light the recycled asphalt and bury the rubber, because the rubber is lighter. We don't want the wind or something to blow the rubber away. So then basically the rubber and the recycled asphalt is being moved to the dryer and mixer. So basically this is the process we have here, trying to make sure the material is consistent, how we really control the quality of construction. Basically starting from the asphalt plant, we make sure the rubber content, recycled asphalt contents, and everything is correct. All right, this is basically the asphalt plant portion. And in the field, of course, on the left-hand side, you see the picture earlier on. This is the paver. So the paver will just make sure the loose mix being placed on the road evenly. And with certain good density, of course, the compactor behind it is going to achieve the goal of the density. So after density is being achieved, of course, we measure the density to make sure they are meeting the requirements. So of course, we really want to make sure the density is going to be good, like 95, 94% of density. So that is basically the field construction. And after construction, you can see the roads is looking pretty good. Okay, so basically the neighborhood really like it, and the public feel like this road is really quiet. And when the public feels quiet, that's something we are trying to measure. Of course, compare with what they have seen now versus they were driving the old pavements, the noise level being reduced quite a bit. And so basically what we have experienced here is we're trying to measure, compare apples to apples. So basically what we're trying to do is compare the new asphalt rubber materials versus new overlay, a conventional overlay. So basically that is basically we can see the noise reduction level is up to 3 dBA. So when your travel speed is 40 miles per hour, which is equivalent to 60 kilometers per hour speed. So basically, you can reduce that one roughly 2.5 dBA. So basically, that's the noise level. It's very convenient, very obvious. And of course, compared with the old pavements, of course, that's basically is a very, very big difference. So anyway, that is basically makes the neighborhood happy. So basically, public really enjoyed it to have this new road. And with the summary, I'd like to really briefly talk about some success we have done here. So one is tremendous progress from modeling to lab work and also to the field practice. This is something very proud of, and we can do a good modeling work. We have accomplished lab work, and then we are going to do field practice. And also in the mixture performance, which has shown really good performance, anywhere from the moisture resistance, low temperature cracking resistance, and noise reduction. All those things are really good. Numerical simulation shows us the stress concentration is not going to be a big problem with rubber, and also high strain and fracture energy has been found. So that is really good thing to see. And for the field projects, we implemented, we can easily recycle, 5,000, 3,500 passenger tires in a given small projects. So basically, we believe there are a lot of potential to implement a lot of recycling rubber in anywhere in the world.